Hello and welcome to the first ever virtual edition of the Spark and AI Summit. In these pandemic times, things are changing so quickly, it's sometimes difficult to know what reality is. And we seek truth. We seek truth in fact, and we seek insights so we can take better actions. That's what I want to talk to you about today, which is how to pull insights from very large amounts of data with Apache Spark very quickly and very cheaply. In particular, how to do this using an open source library called spark-alchemy that my company Swoop created. We call it alchemy because it helps you do magic with Spark, and we'll see how in a moment. I'm the founder and CTO of Swoop, and my company is focused on improving patient outcomes. Particularly, one of the patient populations we care most about are people who have rare diseases. I don't know if you know what a rare disease is, but in the US, the technical definition is a disease that has fewer than 200,000 patients. So these are very low prevalence diseases. And because they're so low prevalence, they're not very common. Doctors don't know how to diagnose them very well. About 30 million people in the US suffer from thousands of different rare diseases. And on average, it takes more than 5 years to diagnose a rare disease. That comes at huge suffering for the patient's family, and at a huge cost for the health system as a whole. One of the things we do with rare diseases is we can predict the likelihood of somebody having a rare disease using some fairly advanced AI models working with petabytes of health and non-health data. But in addition to doing machine learning and AI, we also do a lot of analytics, looking at data, understanding what's happening, looking at changes, making sure that our AI models are doing the right thing. In particular, in COVID times, the change in behavior has sometimes been so rapid that a number of AI models have done poorly. They couldn't adapt to the change. Change like, for example, what happens when the President of the United States recommends an unproven therapy for COVID-19. And our analysis showed up that in one day, prescription volume went up by 50-fold, and they very quickly dropped down. Other times, you want to create interfaces for humans to be able to derive insights from data. Custom interfaces, you can think of it as business intelligence, or in our case, some more unique and custom-tuned interfaces. But the basic idea is to support human decision-making. And when a human is on one side of a user interface, they want the data, they want the queries to produce results at human speed. That typically means sub-second query times. So that creates a problem for us. The problem we have is that on one end, we have petabytes of data, and on the other hand, we need to produce sub-second queries. Spark is not designed for very fast query response times. That's not its purpose. Spark queries have a reasonable startup and finish cost. So we need something in the middle. And the simplest way to think about it is, well, maybe we'll replicate all the data from Spark into some other system, a traditional high-performance database, and then we power business intelligence, all up cube, or a custom web app, or something like that. But that sounds pretty complicated. So let's dig into this problem and see if there are better ways to solve it. Well, let's start with the basics, and don't laugh, but the secret to high-performance analytics is to just process less data. But digging into this actually means four things in the case of Spark. First, it means to process fewer rows of input data. Second, it means to run fewer shuffles. And third, it means that if you run shuffles, you want your shuffles to be as small as possible. The fourth thing, which we'll ignore for the purpose of this talk, is that you also want to make sure that your data is not skewed, that it's evenly distributed. That's an important factor in any distributed system. So how do we approach this problem? Well, typically, the go-to strategy for making things fast is divide and conquer. And in the case of an analytics system, we typically aggregating data, getting from lots of rows to data summarized in a manner that a human can grok. So the aggregation usually involves some type of group by, a rollup, or cube. So if we could break that operation into, say, a pre-aggregation phase that gets done once, and then rather than going to the original data, we could use the pre-aggregated data over and over and over again to satisfy queries. That would be a way to run a lot faster. And the property of data that allows this to happen is its reaggregability. For example, if you're computing minimums or maximums, you can compute intermediate minima and maxima, and then take the minimum and maximum of that, because the minimum of minima is the minimum, and the maximum of maxima is the maximum. Count is a little bit more interesting. When you pre-aggregate with count, you have to reaggregate with sum, because the count of two counts isn't the count of all things. But we have a problem. There's another kind of counting, and that's distinct counting. And the problem with distinct counting is that distinct counts are not reaggregatable. If you have a website and 10 unique visitors visit yesterday and 10 unique visitors visit today, the total number of unique visitors that visit over the 2 days is somewhere between 10 and 20. We can't just add them up. So what do we do in this situation? I mean, it seems like with count distinct, we need to process every single row of the input data to produce a final count for users, and that kind of defeats the purpose of pre-aggregating and reaggregating. So let's dig into this a little more. And to do this, let's look at a specific example. A specific example is a sample of our prescription data related to the COVID analysis I showed you earlier. I pulled, a small sample, just a few columns. Essentially, when a patient visits a doctor on a particular date and a doctor writes a prescription, I pulled the most basic information about that. Just about 10 billion rows, about a fifth of a terabyte. And we're going to process it with a cluster where all this data is going to comfortably fit in RAM, because we don't want to check how fast Spark does I/O to various storage layers. We want to understand how Spark processes this type of data and computes different types of analytic aggregations. Here's the data. You have a date, you have a generic drug name, a branded drug name, a drug code. In the US, that's a national drug code, and in DC, and the doctor and patient IDs, which I've hashed for extra privacy. Pretty simple. So one of the most basic queries we can ask over this data is, what happened to the number of prescriptions, and how many different generic and branded drugs did doctors write prescriptions for per month over some period of time? In this case, the data goes back about 5 years. It's an interesting query because during pandemic times, you don't go to the doctor unless it's really urgent. So we'd expect a reduction in prescriptions and a reduction in the total number of different drugs that doctors are prescribing. And what we can see here is that, we're running a little over 3 minutes. And if we dig into the analysis a little bit further, we'll see that it's, a query that cannot run quickly enough for user needs. So let's apply the pre-aggregation strategy, right? In this case, since we want data by month, we can clearly reduce the date level from days to months. And since we cannot aggregate distinct counts, we can group by the generic name and the branded drug name and essentially preserve their unique values, but still shrink the total number of rows with a group by. Now let's see what happens to our query when we run it again. Wow, with a simple change, we're running 20 times faster. And if we dig in deeper into the analysis of the performance, we see that we've reduced the row count by 850-fold. And we also reduced the shuffle size by 5-fold. Now, the reason for that is essentially because we're processing fewer rows. And so fewer number of distinct values end up on all the workers, so they have to move less data to other workers in the cluster. And the combination of the two is that we run in Spark 20 times faster. Now, if that final query ran a traditional relational database system that's designed for high interactive query response times, so high throughput, it would be a sub-second query because there's so little data to process. But again, we have another kind of problem. And the problem is that we can only do this trick when we're grouping by low cardinality dimensions. There are only a few thousand generic drug names, and then only a few tens of thousands of branded drug names. So we go from 10 billion rows to 5 years times 12 months, 60 unique dates, and at most 10,000 unique values for the branded drugs. I mean, 20-somewhat thousand, tens of thousands. That's an easy trick. We get the 850-fold row reduction. But what if we wanted to get a distinct count of patients? Well, there's more than 300 million patients in the US. So that creates a problem. We know that we couldn't group by the patient ID in addition to everything else. That will hardly cause any reduction in data volume. I mean, how many different doctors do most patients see per day, right? And if we just do a straight computation of a distinct count for patients, we see that the situation gets pretty bad. We're running more than 2 times slower, over 7 minutes. And look at what happened to our shuffle. We're shuffling nearly 150 gigabytes of data in the cluster. Wow, it seems like a lot. The entire data set is about 200 gigabytes. So let's do the math here. Right? Let's say that there are 300 million unique patient IDs, and they're 64-bit integers, so 8 bytes. 300 million times 8 bytes is roughly about 2.5 gigabytes. You have 80 cores in the cluster. 80 times 2.5 gigabytes is an upper limit of about 200 gigabyte shuffle if every single worker had every single unique patient ID. It's a little less than that because one worker is going to keep one set of IDs to process itself and only needs to shuffle the ID set that it's not handling. But you get the idea, right? The upper limit here is close to the size of data we're processing because you have to multiply it by the number of workers in the cluster. And that's where we have a problem. So what can we do about it? Well, if you've dug into the Spark functional library, you'll see that Spark has approximate counting functions. And the documentation says that they can count a little faster. Approximate counting uses a probabilistic data structure called HyperLogLog under the covers, which has some fascinating mathematical properties, and I'll be happy to talk to you about them in the Q&A session after the talk. But let's just try it out. Let's replace the count distinct with an approx count distinct and compute an approximate count of unique patients seeing the doctors. That computation is done at the default 5% error, and we see that we're now running much better. We're running 2 times faster, and the shuffle size has gone way, way down. So let's analyze the situation. So the bad news is we still have to process every single row of input data. The good news is that we have more than 50-fold reduction in the shuffle size. How does this happen? Well, the reason it happens is that approximate counting, rather than exchanging the individual patient IDs, it exchanges a binary data structure known as a HyperLogLog sketch. And a HyperLogLog sketch is a data structure computed by hashing all the IDs that a single worker sees. And it's actually a number of the outputs of a number of different hash functions in the sketch itself. And those sketches, while they can get large if you want low error, are actually pretty small compared to the size of the individual 300 million possible unique patient IDs. We talked about 2.5 gigabytes per worker. And so the net result of good news, bad news is mixed news. We're running 2 times faster, but it's still in the minutes range, and not good enough for the type of queries we want to do. And this is really surprising because under the covers, we seem to have an opportunity to run much faster, right? Like, how could HyperLogLog do what it's doing without shuffling all the patient lists? Clearly, the HyperLogLog sketches must have an interesting property about them that allows them to be combined to compute an approximate distinct count in the reduction phase of the job. Can't we use that ability to combine sketches together in a pre-aggregation reaggregation pattern? The short answer is yes, we can. But for a really unknown reason, the people who implemented HyperLogLog support in Spark for approximate distinct counting didn't actually expose access to the binary data structures. The folks at Google who work on BigQuery, people working on Snowflake, and a number of other systems understood the power of working directly with these HyperLogLog sketches as binary data. And so they provided direct access to them. But for Spark, we actually had to build the spark-alchemy library to do this and add all kinds of other bells and whistles that help you interoperate in ways that are beneficial, which we'll see in a moment. So here's what we can do with spark-alchemy. During the pre-aggregation phase, we can process patient IDs and build HyperLogLog sketches from them. And these are going to be in a binary column and an opaque data structure. But the property of HyperLogLog sketches is they can be merged to create HyperLogLog sketches. So in the reaggregation phase, we will merge the sketches that we created in the pre-aggregation phase into sketches. And then in the presentation phase, we'll actually turn those sketches, the binary data, into a distinct count. And this is what it looks like. Right? On the creation of a HyperLogLog sketch, I use the HLL init agg function from spark-alchemy. We merge with HLL merge, and we turn the sketches into distinct counts with HLL cardinality. So now we finally have a unified framework for working with the typical types of analytics queries and aggregates that we deal with in a pre-aggregate, reaggregate, present pattern. So let's see what the impact of that is. So let's build a pre-aggregated table with HyperLogLog sketches. You see, we just need to change one line in our query. And then let's compute a final query using that pre-computed table. Wow. You know, we're running more than 60 times faster. We're back in the seconds range. If you look at the analysis of what happened, we see that now we have the best of both worlds. We have the 850-fold row reduction on the input side. And on top of that, we have a whopping over 300-fold reduction in shuffle size. The combination of those two pieces of good news is that we run in just a handful of seconds. And again, if this was done in a traditional relational database system, this would be a sub-second query. In other words, we're done. We have a pattern for producing sub-second queries in our analytics system now. In the real world, it's a little bit more complicated because you have many different query types, but we can also create many different pre-aggregate types to handle different query types. One of the things we have to think about, of course, is that we are no longer counting precisely. We have counting approximately. Now, in my experience, sometimes business people get very troubled by the notion of approximate counts. And they ignore the fact that very often the data we work with is not complete, or it's dirty in some way, or it has bias. And you know, when you're approximately counting with very low error, imprecise things, you actually may end up with a better outcome than if you're precisely counting the same imprecise things. You never know. The good news about HyperLogLog approximate counting is that the precision of the algorithm is tunable. It all depends on how many bits of precision you allow in your HyperLogLog sketches. The basic rule of thumb is that to have your error, you need to quadruple the size of your sketch. So if you want less than 1% error at 99% confidence, you have to turn sort of a set of IDs, in this case 64-bit IDs, but it doesn't really matter how large the data is that you're hashing, because even if you're hashing much larger data, it still produces the same HyperLogLog size. And that will become a 32 kilobyte sketch in the largest case. So pretty much for any business need, unless you're dealing with a very tight compliance or transactional financial scenario, you can find an approximate counting approach, mechanism, threshold of error that satisfies same business requirements. There are lots of other benefits to using HyperLogLogs in your production. HyperLogLog data structures are privacy safe. They take potentially unsafe things such as IDs and turn them into opaque binary sketches using one-way hashing. You can perform unions and intersections on HyperLogLog sketches, both across rows and across columns. Unions are lossless. Intersections can increase the error rate. And I'm happy to talk more about this in the Q&A section. The basic idea is that if you're comparing cardinalities that are not too far apart, what's too far, 10 to 1000x maybe, the error is manageable. But if you're comparing things that are many, many orders of magnitude apart in their cardinalities, the error can be quite high. And doing intersections with HyperLogLog in that case is not recommended. And last but not least, with spark-alchemy, you have the ability to interoperate at the binary HyperLogLog sketch level with other systems. In particular, you can do it with Postgres and its clustered version, Citus. And all you have to do is one function call. Instead of HyperLogLog merge, it's HyperLogLog union agg in the Postgres world. So that's all I have for you today. And I want to leave you with a couple calls to action. I really encourage you to take a look at spark-alchemy and see all the different capabilities of HyperLogLog data structures and the native Spark functions that spark-alchemy exposes. And if you're doing any type of distinct counting, you should be thinking about whether you should be doing it approximately with HyperLogLog sketches. If you have to power dashboards or user experiences for business intelligence, for human decision-making, you probably are replicating data out of Spark unnecessarily today. Ask yourself if you can keep most of the data in Spark, and instead of moving raw data, lots more rows out of Spark, you could actually move HyperLogLog sketches. And last but not least, if you care about saving lives and doing it while making Spark great, maybe you should work at Swoop. Let's talk. Thank you so much for your attention. I look forward to your questions.